Are you ready for this? Our first forced harmonic oscillator with a discontinuous forcing function, and we won't do anything too crazy, but a little craziness is going to happen. So here's what we're going to do, is we're going to start with, with a little picture from the textbook. Now, I don't like to steal the book's pictures that often, but this one is just too perfect. Here's our situation. We have a spring on a tilted table, and specifically, what you may or may not notice, depending on how big your screen is, the table's getting tilted because it's standing on a differential equations textbook, specifically the differential equations textbook of this class. So, I thought that was funny. What do we expect? Well, for the first 7 seconds, right, we'll still have oscillation. There will be external forcing due to gravity. So it'll be kind of oscillating. Well, we'll have to find out. Let's get the equation. I'm getting ahead of myself. I just got too excited with the picture. We're going to solve the differential equation y double dot plus 2y dot plus 5 equals h of t. Y of 0 and y prime of 0 are 0. And h of t is going to be the piecewise function, where it's 5 for the first 7 seconds and 0 after that. And we'll rewrite h of t in a second. Okay, so what do we have here? We do have a damped harmonic oscillator. So yeah, we're starting from rest, but it's the spring's rest, right? It's where it would naturally rest if it were flat. So there is that external gravity force, so it is going to be oscillating, and there's going to be like some other, again, this is where it's starting from. It's starting from this kind of rest. But there's really going to be some other rest from the gravity. So it'll be oscillating around some other point. And then after 7 seconds, we kick the book out from under the table. Well, maybe not kick it. That'll be some other impulse forcing, which we haven't gotten to yet. And then, yeah, it will, no longer be oscillating around this further line. It'll start oscillating around what its flat equilibrium would be. Okay, so that's what we can expect from a little bit of qualitative analysis. That's what is happening over here. Before we do a little bit more qualitative analysis, what I want you to do is I want you to rewrite this in terms of our Heaviside function. October, stop climbing on the green screen right now, young lady. While you're doing that, write it in terms of a Heaviside function. What do you think it's going to be? Well, let's compare these two functions, because it's not a super easy question to answer. If we look at the graph of h of t, what is it? Well, something happens when t is 7. Let's plot these. Well, for the first 7 seconds, it's just a constant 5. And then at 7 seconds, it becomes the constant function 0. So it's kind of like the Heaviside function, but not quite. The Heaviside function u of t, u7 of t is the Heaviside function we're going to want. Right, that's 0 for the start, and then it becomes 1. So what's the relationship between these two functions? Well, clearly there's some sort of like reverse nature going on here. And also, h is 5 times what u is. So we can see, okay, right, h is in some sense 5 times what u is. But it's also a little flipped. We need to switch the binary nature of u. Instead of going off to on, we need on to off. So it's going to be 5 times 1 minus u, I think. Because 1 minus u is a Heaviside function with the flipped switch. When it's 1, it's now 0. When it's 0, it's now 1. So it has the flipped behavior, which we want, which is really good. And then it's multiplied by 5, right? So when t is 0, for example, we're at 5, which is what we want. And when t is like 8, we're at 0, which is what we want. Okay, so yeah, this is exactly what we have. So this is going to be h is really 5 times 1 minus this Heaviside function. And writing it in this form will be useful for the Laplace transform. Of course, you could find the Laplace transform of this But let's just use the tools that we already have. So before we do more qualitative, let's jump into the qualitative analysis. Why not? Okay, so qualitative analysis, what do we know about the system? We know the eigenvalues for the homogeneous, the unforced version. If there's no forcing, right, the eigenvalues are going to be -2 plus or minus the square root of 4 minus 20 all over 2. And we could simplify that if we wanted. But well, actually, we do want, because we are going to want to know what that natural frequency is. This is going to be -1 plus or minus, this is -16, which is 4i. 4i over 2 is 2i. Okay, so we see that natural, that 2, which leads us to our natural period of pi. It doesn't really matter because there's no harmonic motion in the forcing function, so we weren't going to get resonance anyway. But we do see that we have an underdamped harmonic oscillator. If there's no forcing, this is underdamped, so we can kind of expect what's going to happen. There's constant forcing at the start and then 0 forcing later. So both portions are going to kind of be underdamped, and they're just going to center around different places. So we might assume that our solution looks like this. Right? It starts by it starts at rest, and the derivative is flat too, so it's going to be starting at the bottom of like a cosine function. And I'll start by like oscillating around here until t equals 7, and then things change and it starts oscillating around the origin. This is kind of what we'd expect. Right, we have an underdamped oscillator up here and then an underdamped oscillator down here. The position will be continuous. Other things might not be continuous. We'll find out. And that's what we should expect as our answer. All right, let's solve it with the Laplace transform. We'll just we'll copy this part and then what what h is. Oh, and our initial conditions. And then we said h of t was 5 times 1 minus u7 of t, our Heaviside function. Okay. To solve it with Laplace transforms, we L both sides. What we're going to get is the Laplace transform of y double dot plus 2 times the Laplace transform of y dot plus 5 Laplace transform of y equals h. Okay, so that'll be the Laplace transform of 5. Actually, let's factor out the 5. 5 times the Laplace transform of 1 minus 5 times the Laplace transform of u7. Now we have a lot going on. Let's break this up into pieces to make things a little bit more manageable. Let's look at the left-hand side and the right-hand side, and we'll start with the right-hand side. Again, it's just much easier to keep things straight when you're not doing 5 things at once. So the right-hand side, that'll be 5 times, what's the Laplace transform of 1? We don't have that explicitly in our notes. But notice 1 is just e to the 0t. So if a is 0, that's what it is. Just 1 over s. So it's 5 times 1 over s, as long as s is positive. Minus 5, oh gosh, I do not like this. Let's make my s's very s-y. Minus 5 times the Laplace transform of u7. When a is 7, this Heaviside function is e to the negative 7s over s. 5e to the negative 7s over s. Being very careful with our 5s and our s's. And we can rewrite that a little bit, but I'm not going to do too much with it. Let's just write this as 5, very clearly a 5 over s, minus 5 e to the negative 7 s over s, like so. And we could maybe combine these depending on what we want to do. Let's keep it for now. Now if we work on the left-hand side, we can use the property for derivatives, saying that the Laplace transform, if you want, you could write down the shortcut for the second derivative. The Laplace transform of the derivative is s times L of y minus y of 0. So this first thing will be s times L of y dot minus y dot of 0. The second thing is 2 times s L of y minus 2 times y of 0. And this last thing is just 5 L of y, which we don't know. We'll be solving for that eventually. Now, luckily, y dot of 0 and y of 0 are both 0. So that's a nice initial condition for us. And we'll use this property again to get s squared minus s times y of 0, which again is still 0, plus 2s L of y plus 5 L of y. And we have a nice quadratic function that we've got here. Oh my gosh, I am really having a hard time today. This should be s squared L of y. So we all have those days where every small mistake will happen 5 million times. So again, this is 0 right here. And we can factor out an L of y. We should get s squared plus 2s plus 5. So that's the good news. The bad news is we need to divide this over because the left-hand side equals the right-hand side. So our equation gives us just L of y equals that right-hand side divided by this polynomial, s times s squared plus 2s plus 5 minus 5e to the negative 7s over s times s squared plus 2s plus 5. And yeah, let's keep these separate. They have a common denominator. We could add them together. But thinking about using the inverse Laplace transform, let's keep these separate for now. Okay, so that's great and all. But now it's time for the inverse Laplace transform to solve for y. And again, we're going to do this in steps because there's a lot going on. It looks like we're going to need partial fractions. Why? Because we have, like, we could complete the square for this parabola, for this quadratic. But even then, we don't have anything with an s times a quadratic. So we're going to need to split this up into something with an s in the denominator and something with this polynomial in the denominator. But we can actually be a little nice. Let's move this exponential over here. Oh, I can't erase it. Let's move the exponential over there because we notice that these other parts are basically the same. So we actually only have to do partial fractions once. So we have that going for us, at least. So let's go off to the side and use partial fractions on each one of these guys. And when we do that, we're going to get that 5 over s times s squared plus 2s plus 5. I should really just make you do this and write down the answer, but we'll show you what this is going to be. All right, this will be some a over s plus bs, tell me about it, plus c over s squared plus 2s plus 5. Multiply by the least common denominator, you'll get a times that polynomial plus bs plus c times s. I'm going to start with the easy stuff. If s is equal to 0, this whole second thing is 0, and we get 5a equals 5. Or 5 equals 5a, if we're really being more precise. So a is 1. That's lovely. How do we find b and c? It's not quite as nice. You could plug in the complex number here and zero it out. Or you could combine like terms. I really don't like the like terms thing. I feel like that's too easy to mess things up. So I'm going to let s be whatever complex number is the root of this. Is this the same thing we've already found, 2s and 5? I think it is, right? Yeah, 2s and 5. It's negative 1 plus 2i will work, right? We'll double check at the end. Hopefully this is it. Then what we get is we get 5. It is the same equation. All right. Now what we get is 5 needs to equal b times s, which is negative 1 plus 2i. Oh, wait, maybe this is not any nicer. Plus c times s. All right, yeah, maybe this is not nicer. All right, this may have been a mistake, but let's run with it. So 5, this becomes negative b plus 2bi plus c times negative 1 plus 2i. Let's just multiply both sides by the conjugate. Negative 1 minus 2i. Now the left-hand side becomes negative 5 minus 10i. And the right-hand side, this just becomes positive 1 plus 4. It just becomes 5. So we'll get negative 5b plus 5c plus 10bi. And that tells us what has to happen. Right? The imaginary part's easier. Negative 10i has to be 10bi. So b must be negative 1. And I'm running out of space, but if b is negative 1, what does the real part look like? Negative 5, this becomes positive 5 plus 5c. So 5c is negative 10, c equals 2. And we check our answer right now. We got y of t is the inverse Laplace transform of this first thing, which we said was a over s, so 1 over s, that's nice, plus bs plus c. Oh, I don't like having the s negative, but we'll keep it there for now. That'll be negative s plus c, which is 2, all over s squared plus 2s plus 5. And then again, we have the same thing, but minus L of the same thing times e to the negative 7s. We'll want to look at those separately too. We do a quick check, and then we'll go to the next page so that there's more room. How do we check this? Well, we should have s squared plus 2s plus 5 over s times that whole thing, plus negative s squared plus 2s over s times that whole thing. Does that equal what we originally had? Hopefully. S squared minus s squared, they cancel. Uh-oh. All right, I think this needs to be a minus too. I think c should have been minus. Yep, it should have been. Great. Our math is right. We just didn't write down the minus sign. And then those will cancel. Since it's minus, just write it like this. It's a good thing to check your work, right? We could have gotten a real pickle there. Okay, cool. We're getting close. Isn't this fun? All right. Next page. Let's do each of these separately too, because there's a lot going on. So first we'll do this first one, and then we'll do the second one. And even this first one is really at least 2 Laplace transforms, right? So the first one is going to be, we'll call it 1. 1 is going to be the inverse Laplace transform of 1 over s, which is not too bad, right? We got something for that. Inverse Laplace transform of 1 over s. Yeah, that's when a is 0. That's just a constant. Minus, this one over here looks a little bit trickier, right? So maybe we should have split it up this way. We're going to have the Laplace transform of s plus 2. We can't factor this, so we can't use partial fractions. We could complete the square. Let's do that. That'll be s plus 1 squared That'll be s squared plus 2s plus 1. So plus 4 like before. Okay. And again, this inverse Laplace transform of 1 over s is just, when a is 0, it's just 1. So it's just going to give us 1 minus over here. What is this? I'm not sure. Because it's close to something we have, right? It's close to this. Oh, no, it's close to the s on top. It's close to the e to the at cosine, right? But we would need an s plus 1 on top. We don't have an s plus 1 on top. So what are we going to do? We're going to look at the inverse Laplace transform of s plus 1 squared, plus 4. But there needs to be another plus 1. So you get 1 over s plus 1 squared plus 4. And why is that nice? Because now on the left, we have this. All right, with a is -1, omega is 2. It's going to be e to the at cosine omega t. And again, this shouldn't be surprising because look at our eigenvalues. Our eigenvalue was -1 plus or minus 2i, right? And the second one is more like this, no? But, oh, okay, we need an omega in the top. Omega squared. All right, so omega is still 2 here. But we need a 2 here, which means we need a 1/2 here. And then we'll be good to go. Omega is 2. A is still -1. And we have e to the at sine omega t. Again, as we would expect. This is really the part of the homogeneous solution. All right, so we're doing pretty good. We have 1 minus, this becomes e to the -t cosine of 2t, and then this becomes plus 1/2 e to the -t sine of 2t, like so. Whew. All right, we got one of them down. Now let's get the other one, which is basically the same, but with an e to the -7s. And we know what that is. We have a property for that. Right? Oh, did I not write this property down? We're looking at the inverse transform. Let's just write a version of this down right here, right? So this is true, right? So if we take the inverse Laplace transform of both sides, we're going to get something really nice. If we take the inverse Laplace transform of both sides, we're going to just get this. And I think changing the brackets is going to mess me up right now, so I'll do that later. And we'll get script L of... Oh, wait, we wanted L inverse. This is what happens when you make things up on the fly. All right, and so we have this. Because we have e to the -as right here, and I'm going to write this all down. Let's write this down, this blue part down, and we'll copy it to the next page. All right, we have the blue part, which is, again, I keep dropping my inverses. We're looking at the inverse Laplace transform of this whole same mess that we had before, which, by the way, we just found how to inverse it. It's 1 over s minus s plus 2 over s squared plus 2s plus 5. It's that whole thing times e to the 7s. And this is not in blue. But we use this property that, oh, this is f of s right here. This right here is some f of s. And we know the inverse Laplace transform of this. We just found it, right? We just found it in red. So we don't actually have to do another crazy inverse Laplace transform. because it's just what we already did in red. They are the exact same thing. And we just use this property to say that, oh, okay, it's just a Heaviside function times whatever we found was the inverse of the red, evaluated at t minus 7. All right, so this is just going to be the Heaviside function u7 of t times all of what we just found evaluated at t minus 7. So that's going to be 1 minus e to the negative t minus 7 cosine of 2 t minus 7 plus 1/2 e to the negative t minus 7 sine of 2 t minus 7. Okay. We're ready to put it all together. You ready for our solution? It's going to take all of this. Because, specifically, it's red minus blue. Red minus blue is what we're going to want. Is our solution. So y of t is going to be red plus 1/2 e to the negative t sine of 2t minus blue, so minus u7 of t bracket 1 minus e to the negative t minus 7 cosine of 2 times t minus 7 plus 1/2 e to the negative t minus 7, and we could have factored out the e's, times sine 2 times t minus 7. Cool. Let's see what this picture looks like. We're going to look at this picture, and we're going to see if it fits our qualitative behavior. All these pages ago, all that work to get something pretty messy that's hopefully just like a underdamped oscillator centering at 5, and then that's suddenly switching to an underdamped oscillator at 7. Let's pull up Desmos, see how we did. Again, you should be able to see that we did get the same solution that we wrote down. I did factor out the e to the negative t minus 7 here, but you do see it's the same. It's not getting graphed yet, so don't be concerned that it doesn't look like that. Ah, look at that. We start, oh, it's, all right, so it's not going to, oh wait, hold on. It's not going to 1, or it's centered at 1. It's fine, because I think that's fine, because of the constant. Let me just double check. But you can see outside of that, right, our initial position is 0. Our initial velocity is also 0. All right, yeah, I double checked. This is right. And so we have these initial conditions being satisfied. We have an underdamped harmonic oscillator. We're getting some oscillations. There's still oscillations here. They're just getting smaller. Furthermore, we see the frequency, or the period, right? The natural period is indeed pi, as we said from our qualitative analysis, right? The bottom of each cosine part is pi. And then suddenly, at time t equals 7, the table shifts. Someone kicks the book out from under the table, and now we have a new underdamped harmonic oscillator, but centering at what was actually 0. And you can see the function is continuous, as we said. Is the derivative continuous, you might wonder? It does look like the derivative is continuous, right? It looks like we're at the top of the cosine right here. If we plot the derivative, here's the derivative of our function, our initial, again, white. Let's not use white. Let's use pink. Pink is the derivative. The derivative starts at 0, which we can see. And then, yeah, the speed is slowing down until at 7, the table tilts and the speed gets bigger again. So the derivative is also continuous. But unlike the position, which has a continuous, which is differentiable here, the derivative is not differentiable at t equals 7. So the acceleration is going to be have a jump, which makes sense. All right, we did it. So I have a couple of things to say here to close out this example of using the Laplace transform for a discontinuous forcing function. Really, what we could have done is just solve two different differential equations. You could have just solved the differential equation for it being 5, and then find out what are the parameters, like the position and speed after 7 seconds, and use that as an initial condition for this second differential equation. So we could have just solved two differential equations. That actually would have been easier here. But the reason why we're doing this is because, again, we're building things up. There will be more complicated forcing functions that we can't do that. There will be things that we want to generalize that we can't generalize if we're just solving this in like n different differential equations. But what we will talk about is what if there are n different discontinuities or infinitely many discontinuities? What's that going to happen? We're not going to want to solve infinitely many differential equations. So we're just building the tools. Even though, again, for this video, did it really need to take 25 minutes? I don't know. But we're building our tool set, we're building our skills, we're getting experience using all of this and using that to solve more complicated problems. And it is kind of nice because even though our final answer is pretty messy, it is really nice to just be able to have this as a single function. I think that's pretty cool. All right. Oh, also, I'm just noticing we could have... No. There's only a couple. There's not that many things we could do to clean this up, just a little bit. We could factor out some common exponentials. But yeah, this is pretty much where we're at. We're going to get to some more cool things in the future. Again, I really think 6.4 is the crowning achievement of this chapter, which is why it's going to be a good section to finish on. But we have more cool stuff that we can do in 6.3 as well. We'll do a sinusoidal forcing function, and then we'll also talk about resonant forcing, which will be fun to see how resonant forcing works with discontinuous forcing functions. But until then, take it easy and bye-bye. Actually, we won't actually have resonant forcing until oh my gosh. Yeah, we won't really have resonant forcing actually until 6.4 for discontinuous forcing functions. And it's not quite resonant forcing in that case, but it has like the behavior of that. But anyway, we will talk about resonant forcing with the Laplace transform later in this section. Bye-bye.